Hey, Cole.
Hey, Jeff.
Sorry, I'm still getting my screen set up. Apparently it's recording, I think. Yeah, I think I've got it recording.
Yeah.
Oh, you can see if it's recording too? That's kind of cool. I didn't realize that. Oh, I
Yeah,
guess I
this
did.
is like in the it says in the top left corner for me.
Oh, yeah, it does. Yeah, okay, yeah. I guess it would. I guess I did know that since you're the one who reminded me last time. Huh? All right, well, I mean, it's almost 5. I guess I'll give it a couple more minutes before people show up.
Yeah.
Did you have specific stuff you wanted to talk about today, or are you just kind of here listening to what people are saying?
Yeah, just kind of here listening to what other people are saying. Did you get my homework submission?
Yeah.
You probably did. Yeah. Okay.
Let's ask you: are you in 131 this semester?
No, I'm not. I decided that I want to take 150 and 160 because yeah, I want to apply to other UCs as well.
What's your major? You're an econ major?
No, I'm a bio major.
Oh, you're a bio major. Okay. Yeah.
Yeah, I also.
You'd want 150, 160 if you were going to do grad school too.
Oh, really?
Yeah, because you're going to you eventually need reasonably complicated calculus if you're doing any sort of serious modeling, and the 130 and 131 really probably isn't sufficient for that.
Okay.
You probably end up needing vector calculus and differential equations, and those are
150,
if you take 131, you don't have the prerequisites for them. So
okay.
Yeah. So
Gotcha. Yeah, I actually had to so 131, or when I decided I wanted to like take 150 and 160, I actually had to take physics 110 and 111 instead of 105 and 106 as well.
Oh, okay.
Yeah, and so I had
110 and 111 they're kind of hard. They're not super simple.
Yeah, I think they cover the same topics as far as like the book is concerned, but just calculus is integrated. And so
in 110 and 111?
Yeah, that's pretty much the only difference. Like I needed calculus in order to switch in. So it was kind of convenient. Yeah.
I didn't even realize that. I thought 110, 111 were the non-calculus version of physics, and then 105, 106 were like the like just purely conceptual, barely any math version of physics.
Yeah, that was pretty much.
Okay.
Yeah.
All right, well, I mean, if you want to ask any questions, go ahead. Nobody else is here.
Sure. I'll pull up my
Oh, hey, Hazel.
Hi, Jeff.
Hey. I have to say I'm impressed that you're like always right on time for these meetings. It's 4 a.m. for you? Is that true?
It's 6:30.
Oh, 6:30. Okay. Okay, that's a little less bad.
It's dedication.
Yeah.
Yeah, I know.
But it's okay. I'm living in California time, so.
Yeah. I imagine your parents are like, it's got to be a little annoying always being up at like 3 a.m. for your trying to do whatever else you're trying to do.
Yeah.
Well, Hazel, Cole said you didn't have all that many questions and kind of just wanted to see what other people had to say. So did you have some questions you wanted to ask?
I have 2 questions for linear regression.
Okay, go for it.
Homework number 74 and 5.
74, 75. Okay.
It's more of the explanation thing, right?
Let me go grab those. Page. Okay, so 74 is the building one?
74 is the yearly coffee consumption, and that's for
Oh, that's
heart
right.
disease.
These are different than they are in the book, huh? Yearly coffee consumption. Wait, I've got my heart rate. Is it before that, I guess? This is regression?
Yeah, regression, linear regression and correlation.
All right, so I've got
74.
life expectancy.
Yeah.
No. That's governmental times. States.
Okay, I think you gotta go.
Buildings. Yearly wine
Oh yeah,
consumption.
76. It's 76.
Okay, wine consumption. Okay, cool.
Yeah.
Sorry, I gotta remember that.
Well, it says coffee consumption in us, but the numbers are the same.
Oh, okay. Okay,
Yeah.
so come on, grab that. Okay.
I've done like A and B.
Okay. Here's the data. Use your calculator.
I want to ask you,
Equation.
what's the difference between least square regression line and just regression line?
Nothing. I just usually don't say least squares because it's just more words. Those are the same thing. Least squares is just the method we find it.
Okay.
Yeah.
So I've done
so A and B. So what do you want to ask about then?
I've got the regression line, but like number C, like explaining words was slope and y-intercept. Like what does y-intercept means in there?
So the y-intercept of your line is where it crosses the y-axis. But the way you really want to think about that, like it's not like, I mean, it is the y-axis, but you really want to think of the y-axis as where x equals 0. And so we're using wine consumption as x and heart disease as y. Is that what you're doing?
Oh, this is linear regression, right?
Yeah.
Oops, I was in the wrong chapter. I was not following.
Okay. So so x is wine consumption and y is death from heart disease. So the y-intercept is what you would expect the death from heart disease rate to be if a country consumed no wine or coffee, I guess. Average per capita wine consumption for countries, I guess. A random sample of 10 countries. Yeah, okay.
Also, y-intercept means that because I thought y-intercept meant the mx plus b. So I thought the b is the y-intercept.
Yeah, that's correct. It's not the b in this in linear regression though. Linear regression typically does a plus bx. So the b that they're talking about in linear regression is the slope.
Yep. So the y-intercept is a.
Let me yeah. So that's what the y-intercept is. It's the prediction for when x equals 0. And so if x equals 0, that's a country that consumes no coffee or no wine, depending on which one you're looking at. And then get a prediction for the death from heart diseases. And like in this case, that prediction probably doesn't mean anything because there are not going to be any countries that consume no wine or no coffee, I guess. Right? And so like, you'll get a number, but you probably shouldn't feel particularly good about that number because a country that consumes no wine or no coffee is not like, that's not a real place. And so the prediction for that is probably irrelevant.
Okay. And like, what is the influential point? Because I know an outlier. What's the influential point?
Where do they talk about influential points?
Like,
oh, there it is. Sorry, I didn't realize that was part of this. An influential point is just a point where if you remove it, the slope changes a lot. It generally means something that's far away from the middle in the x direction. Like an outlier in the X direction
okay.
is generally an influential point, although not always.
Sorry, can you say that again?
Sure, an outlier in the X direction is usually an influential point, though not always. I would guess that this one, this 9.171, is almost certainly an influential point.
That's what I wrote for mine.
Yeah, because it's way away in the X direction, and it's got a very different Y. So this is going to pull the line way down. If you took it out, I bet it would be change the slope a lot. But that's all an influential point is. It's something where it changes the line a lot, and there's no, as far as I know, there's no like mathematical definition of a lot.
Okay.
Let me see if I can. Let me put this data in real quick to the table. 2.5, 2.9. No, that's not right. That's not right. So, were there other questions you wanted to ask?
And then we find like the confidence level, like the significant level of 0.5.
Significance level.
That one we find with the t-test.
Like yeah, for the t-test. Which question are you looking at? Oh,
number
F.
F.
Yeah. It's just it's the p-value you get from doing Lin-Reg t-test to get that one.
Okay. Oh, and then we need to carry like just the Lin-Reg test.
I'm sorry, I didn't understand that, Hazel.
Oh, for F we just do the Lin-Reg test and then the p-value, and then just like reject or don't reject the hypothesis.
Yep.
Okay.
Yeah, you got it.
Okay.
When are all these homeworks due?
This one is due on next Wednesday.
And this one is linear regression, right? And then ANOVA is for Wednesday also?
Oh, sorry. This one should have been turned in this Wednesday, but I'm not being very strict about deadlines. Okay. You're right. It's ANOVA that's due next Wednesday. Sorry.
And then you are posting the exam tomorrow because I couldn't find it anymore.
No, I'm posting it next Friday.
It's next Friday?
Yeah, we have a whole week. So we're finishing up ANOVA this week. So I'm not expecting you guys to like fully understand ANOVA yet. And then after that, there's a little bit of practice time for you to practice on hypothesis testing. I've got a couple worksheets to put up, and then it's the test. And then right after that, it's the final.
So the test is next Friday, and then the final is when?
I'm going to post it on Monday. You have to turn it into me by Wednesday.
I thought it was this weekend.
No, you have another week to practice and study.
Oh.
I mean, sorry.
So yeah, that's good to hear.
Right,
oh wait, I thought we were just having the final.
No, there's a third test.
There's a test? Okay.
Yeah, there's a third
gotcha.
test. I'm having you do that third test over the weekend before the final. Yeah.
Okay. And then is the material on the third test? I'm assuming that's gonna be on the final as well.
Yes, although the final includes a bunch of stuff that's not on the third test. So the final is, in my opinion, actually easier.
Is it cumulative?
Yeah, the final's cumulative.
Gotcha.
Jeff, like I'm still very confused about the chi-square. Like, how do I find the expected frequency?
So it depends on what kind of chi-square you're doing. If you're doing a chi-square goodness of fit, you would
yeah, goodness.
Oh, excuse me, hang on. My computer's being weird here. Okay. If you're doing a goodness of fit, you just take so you know how the hypotheses for goodness of fit have just a list of percentages? It's like P1 equals 20% and P2 equals 30% and P3 is, so you just take those percentages and you multiply them. So those are your expected percentages, because the null hypothesis is kind of what you're expecting to see. And so you just take those percentages and you multiply them by the sample size, because if it's true that P1 is actually 20% and we take a sample size of 100, we would expect to get a count of 20, right? 20% of those 100. So for goodness or fit, that's how you do it. For homogeneity and independence, that's a little more complicated if you want to do it by hand, which I wouldn't recommend. But I would, let me refer you to the chi-square packet for that, because it takes me like a page to explain it in the packet. Switch this chi-square. Right. So if you're looking at these guys, that's right here. Right. So my explanation of it is this. Of why you do that. So let me just refer you to that rather than me trying to explain the whole thing. I can, but I would recommend like just read this and see if you can understand it, because you'll really have to think about it a bit for why this is the calculation that we do. But if you don't understand why it's the calculation that we do, it's okay. Like this is one of the things in this class that, in my opinion, it's nice to understand, but it really won't hurt you if you don't. Like it'll help you maybe understand a little bit better why chi-squared is calculated the way it is. But if you don't get this, it's not the biggest deal in the world.
Okay. So like, can you do one like for me like 72 on the homework question?
72, you mean on the chi-square homework?
Yep.
Sure. Let me get there. Okay. Well, I should switch this back, huh? Looking at this thing. Okay, so 72. Is that, wait, is it actually 72 or is it a different number? No, I mean, is it 72 in the book?
Yep.
It's this one? Okay. Oh yeah, so this one is a little bit tricky because they don't, like the null hypothesis isn't explicitly stated and you have to kind of write it. So 6-sided die is rolled 120 times, fill in the expected frequency column. So we roll it 120 times, what's the probability that we would get a 1 when we roll it?
1 by 6.
Yeah, exactly. So how many 1s are you expecting to roll in 120 rolls?
Would they all be 20?
Yeah.
Okay.
Yeah,
Oh, okay.
we're expecting to get 20 of each one. Now, like obviously we're not thinking we're actually going to get exactly 20 of each one, but that's what probability says is the likely out, or is the most likely outcome for each.
Okay. Yeah. Gotcha. Okay, so I got it.
So our null hypothesis, would it be something like, would it be like the dice is fair?
Yes, that's a fine null hypothesis. If you wanted to write it in sort of the way that we've been doing, that we do the other ones, it would be something like this, right? The null hypothesis is that P1 equals 1/6, P2 equals 1/6, etc. Right?
Okay.
Yeah, something like that. Like this is the way that, like this is the I guess explicit way to write it all out. You don't have to do this. I actually kind of like yours a little bit better, but this is how you you'd write it in the book.
Okay. What about like on a test or on the homework?
Either one of those is fine.
Okay.
They mean the same thing. So
Gotcha.
I'm okay with either one.
Okay.
So then, our degrees of freedom, what else do we need to do? What else do we need? Yeah, would we need to do anything else for this problem besides writing a null and alternative hypothesis?
Well, it said conduct a hypothesis test, so we actually have to calculate chi-squared.
So we have to calculate.
Right.
Okay.
So we have to do observed minus expected squared over expected for each one of these. So you'd have something like, oh, I guess I don't have the thing I wanted here handy. So you'd have to do like observed, which was 15 for the first one, minus expected squared over expected, plus, yeah, you just use the formula, plus observed 29 minus expected squared over expected plus 16. Right, you just do this all the way out. Observed minus expected squared over expected. So a little bit tedious, but you just do this for all 6 of them. And add it all up, and that's your chi-square, or that's your test statistic. And then you use chi-square CDF to find your p-value.
Like I thought like P1 equal P2 equal that is for ANOVA.
No, so ANOVA firstly is about means. And the hypotheses for ANOVA do actually kind of like superficially look like these, right? So your ANOVA hypotheses look something like this, right? Mu1
square, yep.
Mu2
equal M3, yeah.
Equals mu sub k, right? But notice that the big difference here is, well, there's a couple things. One, it's about means instead of proportions. And 2, they all equal each other, not they all equal different numbers, right? So this particular one where they're all equal each other, like that is a goodness of fit test, but they don't all have to be the same thing, right? You could just have, this could be something else entirely where it's like there are 10 numbers in a hat and they're, a 1 and 5 2s and 2 3s and like and 4 4s, something like that. And then and when you draw one out, the probabilities wouldn't all be the same. Right. So these don't have to be equal here. These do have to be equal. That's what ANOVA is checking, is whether or not the probabilities or the means are all equal.
Okay.
Wait, which question is this one?
72.
It's 72 in chi-square. It's the one you asked about last time, Maya.
Oh, so I did that.
Yeah. If this looks familiar, it's because we this is the
it was a little lost because
yeah.
See, I did that one. I was looking for it. For the linear regression, so the table we're going to use, is it going to be the one found in stats?
For linear regression, yes.
So then I put L1 as X and then L2 as Y? Yeah.
I mean, you can rearrange them in other columns. Like you can put L1 in, or you can put X in like L3 and Y in L6 if you want to. You just have to change it when you're doing linreg t-test. Because linreg t-test will ask you for the X value or the X list and the Y list.
Oh, yeah. But it doesn't matter where I put it. I just need to fill that out.
Yeah. I always put the X's in L1, Y's in L2 because it just defaults to that.
Yeah, it's easier. Can we do one so I know how to do them? Because I really don't understand how it works.
Sure. Which one did you want to do?
Can we do 72?
72. Isn't that the one we did last time? Let's. We can do it again.
Or one we haven't done, because I don't know which ones we've done already.
Do you want to do 76? Because I'm having trouble with that too.
Yeah, we can do that one.
Sure. Let me. Sorry, I've done something to my window here that is going to take me a second to fix.
Yeah.
It's become sideways somehow, and I don't know how. I didn't tell it to do that, as far as I know.
Right next to the zoom, where the 100% is. There, maybe?
No, because I'm fitting one full page. That's what I want, actually. I rotated it somehow. No, I didn't.
Is it the button next to the one, like one has one slash?
Like this? I think that just switches pages. Yeah. What on earth?
But in the window.
I'm just gonna do this. Hang on.
Yeah.
I just I'm just gonna go reopen that. I'm not sure what happened there. I'm sure there's some option that I accidentally clicked that's like rotate the screen. All right. Whoa, no.
That's a more key.
This one. All right, so share my screen again. All right, where were we at? That one. Okay. I'm sorry, 76 you said from linear regression?
Yes, please.
Okay. Oh, it's probably not actually 76, is it? It's.
It is, or it's from 70 to then 72, 74, 76.
Okay. So the one we were talking about, like right when you got here, was this one, which I think you said, Hazel said was coffee consumption in her book, and it says wine consumption in mine. Is that the one you were talking about? Because that's the one that's labeled 76 in the book, but I think, let's see, you said 72, so it would be 4 past that? There's nothing that's 4 past that.
In the book, 76 talks about the homicide rate.
Homicide rate, all right. Where's that?
Maybe you're in another chapter.
No, I'm in the right chapter. It's just that you were probably looking at the online version of the book.
Oh yeah.
Yeah, they changed the numbers on me. Or not on me, but they changed the numbers in general, and so it's in here. It's going to be one of these in here somewhere. But no, it's time. No.
It talks about
Homicide rate. There we go. 7. That one.
No.
No. This guy.
Population size.
It's not this one.
It talks about, I don't know, it's different.
Okay. That's the last one.
It says the same thing, but without males. It's just American.
Oh, are they using the same numbers though?
See, yes.
Okay, so they just relabeled their columns but used the same numbers. All right. Okay. Okay, so whether non-white minorities commit a disproportionate number of homicides uses demographic data for homicide rates and the number of the population. Probably just homicide rates and the size of the population. Okay, use your calculator to construct a scatter plot. All right. What should the independent variable be and why? Okay, so which one did you want to ask about there, Maya?
If we can do that one together, so I know how to do all these.
Oh, sure, yeah, we can just do the whole thing. That's fine. Let me.
Because then I'll understand the rest.
Yeah. All right. So I'm gonna turn this off and this off. And oh, you can't see that because I'm sharing it. All right. So I'm doing Desmos here, right? So I'm gonna add a table with the X's and Y's, and I need to shrink this up. Sorry, it's so tight, but I have to put this in 558 724 8.6 538. Oh my God. 0.9 9.9 2 500 457 8.89 442 418 13.07. You already done this in your calculator?
I'm doing it. No, my little sister was playing music. Sorry.
Okay. 6, 7, 6. This is a rather obvious trend that they've made here. There's no way this trend is real.
Mm-hmm.
Right, they've got it strictly as the population goes up, or as the population goes down, the homicide rate goes up. And there's like one more right on the next page. Yeah. Yeah, there's real world data is never this nice. Okay. So the X's are in the hundreds of thousands and the Y's are like 0 to 70. All right. So let's look at from like 300,000 to 600,000. And the Y's go from like 0 to 60. Let's say -5 to 60. All right, so something like that. I really flattened out at the end. Did I do that right? Oh, yeah, I did. That was all these. Sure. That's why 2. 2 a plus bx2.
So you put them in, and then you go to the test, which is the stat test.
Yep. Stat test, Lin-Reg t-test.
T-test or T-interval t-test?
The Lin-Reg t-test, not just t-test.
The linear?
Linear regression t-test, not just t-test. It's all the way at the bottom. There's something called t-test that's like the second one that you don't want. It's the one way at the bottom.
So the linear regression t-int or t-test?
T-test. T-int is t-interval.
Ah.
We're trying to do a test to see if the beta and rho are 0 or not.
Okay, and then it says that.
Probably says X list, Y list, reg EQ. Right. Hazel, you are muted if you're trying to talk.
Oh, sorry. What do we choose? Like for beta and rho, is it not equal to 0?
Yeah, always do not equal to.
Equal to 0. Okay.
Yeah.
Not equal to, and then regular EQ is what?
So that's regression equation. What you want to do is put your cursor there. It should be the like checkerboard cursor thing, and then hit. Yeah, I know. Yeah, and then hit variables. It's the variables button. It's vars. Excuse me. It's labeled vars.
Mm-hmm.
And then go to y vars. So to the right. Choose function, and then y1.
Perfect. And now I just calculate that?
And then hit calculate, yeah. And I would guess that
the P, the DF, A, B, S, R squared, and R.
Yep, exactly. So you probably got a p-value.
Yep.
Right,
It's
and so
5.07.
It's probably 5.07 times 10 to the negative something a lot. Or,
oh yeah, E minus 7.
Yeah. So that p-value is doing, let me go grab let me switch my screen share here. You're doing this test here, right? So, oh, I should have just brought this up, right? So this is, these are the commands for that. The test that you are doing, where did I put it? Is this one. Right, so that's the test that you're doing when you do the t-test for Lin-Reg t-test. And what you're checking, the thing that you really want to read this as, I know it says beta and rho equals 0. That's I mean, in a mathematical sense, that is what you're checking, but this is what it means. It means X and Y are unrelated is what you get for that, for the meaning of that one, and this one is X and Y are related.
So if it's P equals 0 or if P equals 0, then X and Y are unrelated?
P equals 0. You mean rho?
Yeah.
You mean this thing? That's actually a rho. That's actually a Greek R.
Okay.
Remember that. So R. Remember that R is your correlation coefficient. It's the statistic that you make to show you how tightly clustered around the line your points are.
Okay.
And so if that's 0, it means that they're unrelated, that there's no correlation between X and Y. And that's for R. Rho is just the population version of that. So it's saying, okay, well, if we had all the possible data, like so in this case, we found the homicide rates and the populations for like every city in the world that's ever existed. What would the correlation between population and homicide rate be? And if the answer is that there's no correlation between them, then we don't want to use linear regression to attempt to predict it, because that wouldn't make any sense. So they're unrelated, so you can't predict one with the other. Which is why the thing that you got of 5 point something times 10 to the negative 7th, you said, is important here. Like, that tells us that we want to reject the null hypothesis, and the null hypothesis is that they're unrelated. We're rejecting that in favor of saying that we are pretty sure that those two things, population and homicide rate, are related, and that it's reasonable to predict one by using the other one.
And when we're answering the questions, do we have to answer them with all the all the questions?
Probably. Let me look at this.
Like, what should the independent variable be, and like, should we answer all those things?
Yeah, you should answer that for sure. So in this case, what do you think which should be the independent variable and which one should be the dependent variable?
The independent is going to be la independiente se quiso una idea. Wait, para. The independent is going to be the homicide rate.
So I would think it would be the other way around.
Yeah, the population size, and then the dependent one is going to be the homicide.
Right. Yeah, you want to think of independent as the one that is causing the other one to happen. Right. Okay. So we're thinking that in this case, a smaller population means a bigger homicide rate, which doesn't sound correct, but. Wait, he uses demographic data from Detroit, Michigan. What? Are these different years?
Probably.
These are all Detroit. Oh, okay. So I hope they ask a question about why this is
like 1.04 multiplied 10 to the power minus 5.
I'm sorry, say it again, Hazel.
No, my p-value is 1.04 multiplied 10 to the power minus 5. It's not 5.
So Maya, did you do greater than, or did you do not equal to for your Linreg t-test?
Not equal to.
Wait, let me check.
Are you sure? Could you guys both check? I don't have something that'll do a hypothesis test. Because I think, like, the fact that one of those is 2 times the other one means that.
You mean the p-value or the r value?
The p-value. R is like negative 0.95.
Oh, cool. What did you?
Beta, B, or whatever.
Beta and rho. Yeah, not equal to?
Not equal to.
Okay.
And then the the reg is Y1.
Right. That could be anything that won't affect the results.
So did you put the data from the book or from here? Because it's a little different.
Oh.
From the book.
Okay.
So I mean, if they're a little bit different, then you're going to get slightly different results.
What did you get for your T and your P? Hello?
I think she's reading. Hang on. So I'll be honest, it probably isn't that big a deal. Most likely you guys are just using slightly different data one way or the other, maybe from different versions of the book or whatever. The important thing is how you interpret that, right? And so when you're answering what should the independent variable be, like it should be population size, because that's the thing that we're thinking predicts the homicide rate. Whoop, Hazel cut out. I wonder if she lost connection. Let's see, add this to your scatter plot. Okay, so were you able to do part B, Maya?
No, I don't know how to do that.
So since you hit reg EQ equals Y1, it should have stored your regression equation. Hit Y equals in your calculator. And is plot 1 on as well as Y1, which is probably the equation we found? Yeah, so if you just hit graph, it should do that. It should do part B.
No. Sorry, Jeff. I was saying like there's a little difference in the numbers between the book and this one and the one you're sharing.
Yeah, that's probably the difference in the R's. Like that's not the hugest deal.
Well, it's the p-value, but it's okay because we have to reject it anyways.
Yeah, it's exactly like it's the same. It's kind of the same result. Maya, do you see your points and your line on the same graph now? Try zoom and then zoom stat, which is number 9.
Oh, there it is.
Okay.
And now I put Y in the graph. Yeah, there I have it. Okay,
cool. All right, so let's see what these things mean, because in my opinion, this is the most important question, talking about what these things mean in this context, because that's what the model is. That's what models are for. So they're supposed to tell you something about reality. And so the meaning of the various numbers that we get should tell us something about, I guess, Detroit. Hey, wait a minute. Is that the right size of Detroit? Anyway. So slope of the regression equation. So the slope that I had was like negative 0.00002. So something negative, something small and negative. So how would we interpret the slope in this context?
What's going down? So it's
like
So you want to think of slope whenever you're doing regression as it's how much we would expect Y to change if X changed by 1.
Okay.
Also, the higher the Y, go ahead. That's right. The more the X, the higher the Y.
No, I think so. Let's see here. So here's what I'm seeing. I'm seeing a graph that looks like this, right? So the bigger the X, the smaller the Y in this case.
Yep.
Right. And so we're thinking of, so I want to think of population so if X increases by 1, that means that the population goes up by 1 person, right? Because X is population. And then the question is asking, okay, well, what then happens to Y? And for us, for our data, it looks like y goes down by a little bit, 0.00024. Right, so the way I would interpret the slope is that for every increase in one person, for every increase in population of one person, we expect the homicide rate to decline slightly by negative 0.0024%. You could also write that a little bit differently and say that, like, if the population increased by 10,000, that we would expect the homicide rate to go down by 2.4%.
Okay.
But that's the way you always want to interpret the slope is, if x increases by 1, what happens to y? And then you just put that in plain English, right? Instead of x and y, you say, okay, if the population increases by 1, then the homicide rate decreases by this much.
Okay. So the y-intercept is like, the y-intercept would be...
No!
You all right there, Maya?
Oh yes, I had to sneeze.
Oh, that was a sneeze. I thought you were like yelling at your sister. Okay. I'm sorry, Hazel, what were you saying?
Yeah, the y-intercept would be 141 point, something like.
Yeah, 134.5 is what I have, but we probably have slightly different data, but yes.
Mm-hmm.
Yeah, so what does that mean? And the meaning is going to be a little hard to interpret in this context. It's a little ridiculous.
What do you have?
So it's like, because you said the prediction 1x is equal to 0, right?
Correct. Yeah, that's exactly what it is. So what does x equals 0 mean in this problem?
X equals 0 mean like the the population size is 0.
Right. And so the thing that we get, then it's the prediction of y. So we get, I have 134.5 is my y value. And remember that y is the homicide rate per 100,000 people. Right? So it makes no sense in this context.
Yeah.
Right? So it's saying that if the population was 0, then we would expect the homicide rate to be 134.5, which is nonsense, right? There's no people. You can't have a homicide rate of 134.5. It makes no sense at all. And so this is an example of like way too much extrapolation. Like you would never use the model to predict the murder rate for a population of 0 because this just doesn't make any sense. Okay. And so this is not like it's nonsense. The y-intercept of the regression equation. Like that's what it means. That's what it means in context, but it has no actual real world meaning.
So what do we write? We just write like there's no actual meaning.
I would explain what it would be like if it had a meaning, right? It would be the homicide rate when there were 0 people.
Okay.
We would expect the homicide rate for 0, or the model predicts that the homicide rate for 0 people, or in a city with 0, or in Detroit, if Detroit had no people in it, the homicide rate would be whatever you got, 141 or something like that per 100,000, which is complete nonsense, right? That makes no sense for a whole bunch of reasons. It's a weird question too.
So the correlation R is like the number R.
Yeah, so it's the R that we got. Mine was negative 0.95.
0.93, yeah, something.
Yeah. Let me jump over C3 for a second and say that the correlation coefficient R doesn't usually have a real world meaning. And it doesn't in this case either. R squared does. Like this actually does mean something, but not just R. R doesn't do that. That's weird that they would ask that.
R squared would be like the 87% was based on the crime rate, like right, something like that.
So something like that. So remember that you. Oh, I didn't switch my sharing. I want to look at this here. So R squared is this, right? So it's the percentage of the variation in the y's explained by the relationship between x and y. So do you remember that when I was doing this this lecture last week, Joel asked about this question, right? Joel asked about how to interpret the R squared, and so the y values, like if you look at the y values here, right? If we look at just the y values, I picture taking all of these points and like smashing them onto the y-axis, so they're just points in a vertical. Oh, you can't see that. So we just take like all these points and put them in a vertical line, basically, right? Then they stretch from here down to there, right, along this line. There's variation in the y values there, but it's not that they're just randomly, like that they didn't just randomly show up in here or in this line. They showed up there. Where they showed up is partly due to the fact that there is this trend, right? The further to the right we went, the lower they got. And so some of the variation in where the y's are is random, and some of it is due to this trend. So R squared is the percentage of the variation that's due to the trend. So in this case, an R squared of I have a 0.907, tells me, I'll call this 91%, tells me that 91% of the variation in the y's, so how spread out the y's are, is due to the relationship between the y's and the x's, the population in this case, and about 9% is due to other factors.
Yep.
Right, and so that's what R squared is telling you. It's telling you the percentage of the variation in the y's that is due to the linear relationship between x and y, and then 1 minus that is the percentage in the variation in the y's due to other factors.
So like how about for R? Like how about for R? How will we?
As far as I know, R does not have a nice real world meaning in this case.
Yeah, it just says like it's significant or not.
Oh, well, R doesn't tell us whether something is significant, right? The test that we're doing that involves rho or that involves R does tell us that, but that's not like the real world interpretation of R, right? They said discuss what R means in context, and I don't actually know what they are looking for there. I mean, this is 78. If I go to the answers, do they have that one? Probably not. No, they do. They do odds up to there. All right. So I actually don't even know what they're looking for there, to be honest. But as far as I'm concerned, R does not really have a real world meaning. It's just it's a statistic that we construct that tells us something. It tells us how tightly correlated the data is with the line, but that's it, or the strength of the correlation between x and y. But it doesn't do it in any sort of like percentage way or anything like that. It's just a number that we sort of compare to other R's to see how correlated things are, right? And so this is quite tightly correlated. Like the data really does follow the line pretty well, although the fact that it's, you know, getting bigger here, or that it's kind of leveled out here, sort of suggests to me that maybe a line isn't the best, isn't actually the best way to represent this data. Kind of looks like it might be exponential.
Yep. Okay.
I curious what they
So just to sum it up, the slope of the regression when x is smaller than y is also smaller because they are related.
I'm sorry. Could you say? I didn't quite follow what you were saying there.
For the slope of the regression, how would you explain that?
So the slope of the regression is how much. The slope of the regression is how much y changes if x changes by 1. So in this case, that's. I had a negative. Sorry, I'm messing around with Desmos here, and I should be answering your question. So the slope of the regression line here is like negative 0.00024. So you want to think about what x and y mean, and then just say in plain English that if x increases by 1, we expect y to change by the slope. So if x increases by 1, that means the population went up by 1 person. We would expect that the homicide rate would go down by this tiny amount, 0.00024 people per 100,000.
Okay, I just didn't understand that. And then that value is gonna be, how would I know that value?
How would you know the slope?
Yeah.
You read it off your regression, right? You've got it stored in your calculator. It's the slope of the line in your calculator.
It just doesn't show me any values. I'm just really lost.
It does show you what the values are. So if you hit y equals, you should see the equation of your regression line, right? And then the slope is the coefficient of x, right? So you probably saw this number right here, right? Your regression line is probably like 134.514 minus, or it probably says plus negative 0.00024175x, right? Okay. So the coefficient of x is the slope.
Ah.
Yeah.
This is hard. Okay, I understood.
Okay.
And then the y-interception is going to be in there.
Yeah, so the y-intercept is the constant.
It's A?
Yeah, it's A, 134.514.
I need to write those things just to know. And then the slope is in A plus BX.
Yeah, it's the B in A plus BX.
Just the B?
Yeah, just B.
Ah, now I get it. Ja. Okay, got that. And then, so the conclusion is going to be that they are related.
Yes, although it's not the A and the B that tell you that. It's the p-value that you got.
Yeah, p-value is going to be smaller than alpha, which means we reject HO. Therefore, then data does provide convincing evidence that there's a linear relationship between them.
Jeff, like not a linear regression question, it was like a chi-square question. Like for the hypothesis, right? If we write like the dice is fair for null, like should we just write like the dice is not fair for alternative?
Right.
Yeah.
Yes.
Okay. Also, for this 7-year, I won't explain what R is. Is it okay?
Yeah, so you might just want to say something like, R doesn't have a real world explanation, right? Instead of omitting it, it's better to just say like, I see you're asking that, but this, as far as I know, this has no meaning.
Yeah. Okay. Like we're rejecting the
there it is.
rejecting the null hypothesis because it's we're not rejecting the null hypothesis. So there's there is linear relationship between population size and homicide, right?
Yes, there is a linear relationship, but we are rejecting the null hypothesis. Because remember, the null hypothesis is, where'd it go? Where did I put it? This, right? That's what your hypotheses are. The null hypothesis is that X and Y are not related, that they're independent of each other. The alternative is that they are related. And so when we reject the null hypothesis, we think they are related.
Oh, okay. Okay.
When the dots in the graph are all scattered and separated, and is that going to influence on the? No, don't listen to me. Whatever.
Okay. It sounded like you were asking, like, if the graph was kind of randomly distributed and sort of like just sort of everywhere in a cloud.
Yeah.
Yeah, you'll end up getting a p-value that's big in that case.
If they're all like all over.
Yeah, instead of following a nice trend like this, what you'll get is a p-value that's big, and it'll make you not reject the null hypothesis. Oh, you can't see what I'm pointing at. Gosh darn it, I didn't switch. Right, so if instead of this nice trend here, there was just like this sort of cloud of points in the middle, the thing that you would get, you wouldn't get a p-value of whatever you got, 5.07 times 10 to the negative 7 or something like that. That you would get a p-value of like 0.4. And then that would tell you that we think that the data that X and Y are unrelated, right? That would make us not want to reject the null hypothesis when you got a big p-value. We would think that X and Y are unrelated and that there's no actual relationship between them.
So for number for 17 to 19, 17 is going to be linear, strong, and positive.
17 to 19, is that one of the problems in the book?
Yeah.
I don't know. Let me see here.
Because it's like all together and they go up, so it's positive. And then 18 is a little scattered, but it still looks like they're still a little bunched together.
Still negative, yeah. So yes, oh yeah, I agree. Strong positive linear for 17.
But it's weaker.
Yes, probably they say strong or weak. I would say that's moderate, right? That's a pretty clear trend that as Y gets bigger, as X gets bigger, Y gets smaller. But it's not as strong as it is in 17. So I would say that's moderate. This isn't even weak. And then 19 is an example of what you were talking about, right? No correlation between X and Y here, right? There's no trend that has one that does anything, that tells you anything there. Yeah, so strong positive, moderate negative, no correlation.
Linear, strong, positive, linear, moderate, negative, and no correlation.
Yeah.
Yola.
Can I write weak instead of like moderate? Or
Sure. Yeah, you can say weak instead of moderate. I'm just trying to give you a sense of like if we actually calculated this, this would probably have an R of about 0.5, something like that.
Yeah. Okay.
Right. That's a medium R. Yeah.
Yeah. Okay.
Or I guess the R would be like negative 0.5, not 0.5.
Okay. Oh wait, I wanted to ask you that one question on ANOVA because I was confused, but I cannot find that. ANOVA.
Was it like a homework question, or was it like a topic question? Like, could you explain more of more of how to test the hypotheses or something like that?
No, it
was a homework question.
It's a homework question. Just.
Oh. Okay.
But you don't remember which one it was?
Oh no, it's like the 51 that you said, like, is this claim true? That one, what does it mean? I wanted to ask.
Okay. So here we go. Is the claim accurate? Oh yeah, it's this one. The one where I put the little double asterisk saying, they say, is the claim accurate even though they made two claims. So okay, so two workers commute from the same building. They are interested in whether or not there is variation in the time it takes them to drive to work. They each record their times for 20 commutes. The first worker's times have a variance of 12.1. Second worker's times have a variance of 16.9. The first worker thinks that he is more consistent with his commute times and that his commute time is shorter. Test the claim at the 10% level. Okay, so they made two claims here. Claim number one, he is more consistent, and claim number two, his commute time is shorter. Right, and those are entirely different things. You could certainly have, like, it could certainly be, one's true and not the other one. Now, they didn't give you information to calculate, to do the shorter one, right? So the commute time is shorter is untestable because they didn't tell us the mean. So that's not the claim we're talking about. It has to be more consistent with his commute times, right? That's the thing we're testing. So the two sample F test, right? S1 is 12.1, S2 is 16.9, and the alternative hypothesis is that S1 is less than S, or sigma 1 is less than sigma 2.
Yep. So like I want. Oh wait. What does more consistent mean? Like, more consistent mean better?
More consistent means less variation. So somebody who, like, so if I had, let's say I have these two people, and I'm just going to make these up. The first one takes 20 minutes, 21 minutes, 20 minutes, 20 minutes, 21 minutes, 20 minutes, like almost the same thing every time. The other guy takes like 10 minutes, 35 minutes, 27 minutes, 9 minutes, 42 minutes, right? That first one, those means are probably about the same. I tried to pick means that are about the same, but the first one is much more consistent than the second one. The second one is very inconsistent, right? Sometimes it's 9 minutes, sometimes it's 40 minutes. Yeah. And in this case, the way you would measure consistency is via standard deviation or variance, either one, right? So the first one has very low standard deviation. You get almost the same thing every time. It's very consistent. Second one has very high standard deviation because you get a wide variety of different things.
Okay.
And that's what a two sample F test is testing, is that is one variance equal to the other one or bigger or smaller depending on how you write your hypothesis.
Okay. Yep, I got it.
Okay, cool.
That's all I have for now.
Okay. How about you, Maya? Do you have other questions you wanted to ask?
No, I was just checking to see because I know it, but it is still a little confusing for the dependent and independent. So I'm going to start number 17 and then choose what's what.
Okay. Well, I can stick around for a couple minutes while you start that in case you want to ask some more questions. Cole, did you have anything else? You've just been kind of sitting there muted for a while. I know you were just listening to what everybody had to say.
Yeah, just been listening.
Okay.
Yeah, just kind of tagging in along.
Okay. Cool. So I'm perfectly happy just sitting here for a couple minutes while you guys start on a problem if you want to. See if you want to ask any questions. But other than that, I think you're good.
Just to know, the format for all the questions for linear regression is the same as the one we did for 76.
I'm sorry, did you say the format?
Like how we answer them, like the rate. Is it always
pretty much.
the same?
So it's a little bit. So linear regression is a little bit different than like hypothesis tests that have like a clear, do you reject the null or not reject the null? Linear regression is more complicated in the sense that what you're doing is you're building a model and then using that model to make predictions. And so there's like a lot of different questions that you can ask in regression. They kind of don't all look the same. I would say that they typically look something like this guy, right? Where there's a bunch of parts and those parts are usually like, find the regression, or does this look linear? Find the regression line, make a prediction. Is this significant? Interpret the slope, right? There's a bunch of stuff you can ask. So for an indication of what those kind of questions look like, let me refer you to the quiz I posted in Quizzes About Linear Regression, and then also the practice test that I posted in Canvas, which has a linear regression question. It looks pretty much like this, right? It's a bunch of parts and it asks you to interpret the various.
But we also answer them. We always answer them like in the same way. That's
pretty much, yeah,
like
yeah.
With like putting the table and then doing the graph and then putting the
yes
S&P test. It's always
yes,
like
pretty that. You all that stuff is the same, yes.
Okay, and then the p-value thing is always the same. Like if it's smaller than you do that.
Yeah, and then if the p-value is smaller than 0.05, then we say that the correlation is significant. If it's not, then we say that it's not. Yeah. Yep.
Perfect. Okay, so that's okay. And then, Olivia, parate. Parate. Sorry. And then, ANOVA we're gonna do on Monday.
ANOVA we did on Wednesday, right? There was the lecture on ANOVA. The homework the homework is due next Wednesday. We can talk about it more on Monday though, for sure. On Monday I'm totally planning on talking about it more.
Yeah, but we
a little bit confused.
I thought the exam was this weekend and then the final exam was next.
No, so the third exam is over next weekend. Not this next one, not like today, but like next Friday is when I'm going to post it. And then the final I'll post on Monday and you'll have till Wednesday to finish it.
Oh, okay. And then this Monday, like what do we have a Zoom lesson?
Yeah. I mean, we don't have a Zoom, we don't have a lecture per se. We have kind of more like this where I'm just going to answer questions and maybe expand on it a little bit.
Oh, perfect.
But that's it. Yeah. And then the rest of that week or the rest of next week is just you guys practicing stuff, getting ready for the test, and then the test's on Friday, and then the finals on next Monday.
Okay.
Cool. So did you have any other questions that you guys wanted to ask?
Nope.
Cool. All right. I think I will end the meeting and post this thing to Facebook, or not to Facebook, to YouTube.
Perfect. Thank you.
Great. It was nice seeing you
Thanks,
guys.
Jeff.
I will see you on Monday. Have a good
Okay,
weekend.
see you.
And
Bye.
Thank you.